Compiler construction number 7. This is a relatively fast thing. So what we did last time is we wrote the color function. So recall that what color does is it takes the variables and the interference graph combined with the initial coloring, combined with the move graph, and then what it does is it produces a new assignment. So how do we actually integrate all this into our code? Basically what we're going to do is we're going to say something like, let v0 equal the variables in the program. And this is what uncover local computed. Okay. Then what we're going to do is we're going to compute I by doing, what did I call it? I called it build interferences. Build interferences. And really I got I and M from this. So let me just erase part of this. So we got I and M. We got build interferences on the program. Okay, and it's going to give us back the interference graph and M. Then what we're going to do is we're going to construct V by saying we're going to take V0 and we're going to add in all the registers. All the registers. Now, when I say all the registers, I mean, RBX, RAX, etc. We're gonna add all those in. Then what we're gonna do is we are going to say that row 0 is going to equal the empty set with an additional mapping where R0 is going to go to 0 up through R3 is going to go to 3 and R15 is going to go to 15. Now, as an aside, in that previous discussion, we're acting as though you can use RAX. And it is good to be able to use RAX. But it turns out for kind of a weird reason, we actually can't really use RAX ever. And it's kind of complicated why to say this. But remember patch? What patch does is it looks at situations where there are two instructions that could both look at memory. Since both things could look at memory, that means that they might end up looking at memory. And if they both look at memory, then that means that we're going to move one into RAX and pull the other one out. So what that means is that we essentially have to treat every instruction as one that might look at RAX. That is any instruction that has two arguments. And so there's kind of two ways that you can implement this. One way is to just pretend that RAX doesn't exist. And if RAX doesn't exist, then that basically means that we don't say that R0 equals 0, we say that R1 equals 0, and R2 equals 1, and so on. And you just make it so that your register allocator just completely ignores the fact that RAX is a register. The other way to do it is to go back into our interference graph construction. And what we would do is anytime there were an instruction that took that had two registers, two arguments, we would basically say, we would conservatively assume that it writes to RAX and reads from it. If it writes to RAX, because the thing is that we would have move XY, and we might have to turn that into move X into A, into the register A, and then read A and Y. So that means that we would basically treat every instruction that has two arguments as if it also read and wrote RAX. And right now the only instructions that do that are add Q and move Q, so we could do that if we wanted. Okay, so we've now set v0, im, v, sigma 0. So then what we'll do is we'll say that sigma equals calling color on v, I, sigma 0, and m, or sorry, row 0. All right, so now we have our renaming. Then what we're going to do is we're going to compute n, and n is the maximum value in in row. So we're going to look at what comes back, and we're going to say which is the highest number that we ever actually used. And now what we need to do is we need to construct a new mapping that goes from these numbers C. C, by the way, if I feel like I've said this many times, it's really just a number, right? We say color, but it's not. It's really a number. Okay. So then what we do is we can use this to produce sigma. And sigma is the following. So sigma starts off as empty. And what we do is we say for I equals 0 through 12, and R equals RBX through R15. I'm going to do the thing where I assume that it doesn't exist. We're going to say that sigma of I equals R. Then what we're going to do is we're going to say for I equals 13 to n, which remember is the biggest number. What we're going to do there is we're going to say that sigma of I is going to equal RBP, that's the base pointer, and then 8 times I minus 12. Okay, so what this is doing is it's saying that the first 13 colors, they're going to be registers. And then all the registers after, all the colors after that, they're going to be stack locations. By the way, you may want to, right here, say the odd or even, right? And if it's even, you leave it alone. And if it's odd, then you add 1 to it, because we need to make sure that n, no matter what, is even. Remember how we talked about this, that the stacks have to be aligned? Okay, now this produces this mapping called sigma, which maps to all of these things. Okay, so now what do we do with sigma? The thing that we do with sigma is we walk through the program and replace all of the variables. So we'll call this v2. And what we're going to do is we're going to generalize assign homes. So remember what assign homes did is it walked through and it replaced something, it like knew what number it was. I believe that previously what it did is it took a variable and it turned it into a number. What we're going to do is we're going to change that. So instead, it's going to take a variable and turn it into an arg, and we're just going to call it with sigma. And now what that's going to do is it's going to walk through our program and assign everything. Okay, then what we're going to do is we're going to add another rule to patch. Remember that what patch does is it walks through our code and it replaces sequence of its instructions. So what we're going to do is we're going to say that if there's a move queue where we have x moving into x, then we're going to replace that with nothing. So we're going to notice when assign homes, assign two things to be the same thing, and we're just going to delete that. Okay, so this is step 1, step 2. Okay, now there's one more thing that we need to do, which is that we need to change the way that our main generation worked. Remember that we had this main generation step, that that updated the stack. It looked something like this. So this is inside of main. It looks something like begin would point to push Q RBP to save that. Then it would say move Q the stack pointer into the base pointer. Then what it would do is it would jump to the body. No, sorry. Then what it would do is it would subtract the stack space from RSP, and then it would jump to the body. And then what end would do, while I'm off screen, then what end would do is it would do an add Q of SS to RSP, and then it would pop Q the RBP. Okay, so that was what our main thing used to do. What we're going to do is we're going to modify this in the following way. And let me do something fancy. There, what we'll do is we will take this right here, and we'll move it down to there. And then we'll take this and move it down to there. Okay, we're going to make space. Okay, now what we're going to do right here is we're going to push Q on R12, and we're going to push Q on R13, and so on. We're going to push Q on all the call E saved registers. And you can look inside of the assembly guide to remember which ones those are. And then down here, we're going to pop all those off. We're going to pop Q in the opposite order. So I'm going to write R13 and then R12. I'm going to write ... and then R12, 13. So now what we're going to do is we're going to pop Q all of the call E saved registers. Now what we're doing here is that since we just got called, we are going to use these registers. And so since we're going to use them, we need to save them to make sure that the previous values that were in them get restored. Now, values that are not ours, the values that we don't care about, what am I trying to say? It's not that we don't care about them, it's that we don't push every single register, because some registers, they were saved by the caller. And since the caller saved them, we don't need to push those because they already remember them. Now, you may ask yourself, why didn't we do this push and popping thing when we generated calls ourselves? And the reason we didn't do that is because what we actually did is we made it so that call instructions interfere with those registers. And since they interfere with those registers, that means that everything that is live at the point of a call can't be inside of one of those registers. This is potentially a bad thing, because it means that the things that persist in our code across call sites will never be in those registers. Which means that if we have more of them than fit inside of the registers, then we just won't use them. What we could do is we could instead make it so that they could be anything, and then just record inside of a call which registers were active at this time, so we push those ones and restore them afterwards. But the way that I've described it is simpler than that, but that way is sort of the typical way of doing register allocation. All right, so after this, we have now made a compiler that actually uses, like a real graph coloring algorithm and makes something, quite reasonably efficient. But notice that our language is really, really simple, right? We still only have negation and addition. Now, obviously, you could make it a little bit more complicated by adding other arithmetic operations, but it's not quite interesting enough. So what we're going to do next time is we're going to actually add a new kind of data type. We're going to add booleans, And by adding booleans, we'll add boolean producing and consuming operations, like if, sim, is, and whatnot. So hang in and we'll make our language more complicated and interesting.